So this is a story about one of the homework problems. Um, in one of the homework problems, I ask you to estimate the basically the typical total error you see in a machine instrument, and the machine has two sources of error. The story is that there's a drill bit that's placed on a part, and there's two sources of error, so the drill bit doesn't always hit in the right place. Um, so how far on average is the drill bit going to land from where you want it to, given these two errors? And so you can talk about the problem in terms of vectors. Um, so from the problem, maybe you remember that there's a total error, and it comes from error 1 and error 2. And these are both two-dimensional. And so I want to find the average value of this r. Now, you should work it out, basically the triangle, that allows you to say that this average value of r is the root of a squared plus b squared plus this cross term. Um, this is related to something called the law of cosines, if you'd like. One way to do an average mathematically, you may not have heard this yet in calculus, is if you have a function like sine theta and you want to average it between 0 and pi. So I remind you of what sine theta looks like from 0 to pi. So if you want to average it, you do something called an integral. And an integral is a way of finding basically the area underneath this function. So you've got kind of this bump. So how much area is in this region? That's what the integral does. And then if you want to find the average, you need to divide by how much basically space you're averaging over. So I'm only averaging over the first half wave of the sine curve. So I'm dividing by pi because that's how long this is. So if you haven't learned how to do integrals yet, Mathematica, which the university has a site license for, is a great way of doing integrals quickly. Um, and the machine looks kind of like this. If you open up Mathematica under Palette, there's a classroom assistant. And in the classroom assistant, there's an integral right here. So you get this thing. So you're integrating from the lower bound to the upper bound. You're integrating some kind of function, and you're integrating over some variable. And normally this function is a function of this variable. So let me show you how it works. So I'm going to integrate this. And, Mathematica, I'm not a wizard. I just use it. So I'm just going to click yes. So the integral turns out to be 2 over pi. And if you've taken most of Calculus 1, you get to a place where this is, a pretty straightforward deal to do. Let's see. So 2 over pi. What is that? 2 divided by pi. So pi is about 3. So this is going to be about 0.6. There's another thing in Mathematica. You can work out what expressions that are perfect are in base 10. And that's this function, this slash slash n, and percent is the last result. So it works out to be 0.63, roughly. Now, you can also edit Mathematica notebooks. So that's what I'm doing right now. I'm going to throw in 0.63, right, because that's what I think the average value is, and that's what the integral tells me the average value is. And if I do Shift-Enter, look, the orange line is this 0.63. That kind of looks like the average value, right? For half the time you're above, for half the time you're below. Seems right. So remember, we're not trying to average sine. We're trying to average this radius. So to average this radius, we've got to do the same deal, right? So 2 pi is the region that we're averaging over. So we're going to divide by it. And we're going to integrate from 0 to 2 pi because that's the region we're averaging over. We're going to integrate over theta. So that's this d theta thing. And then this square root deal, that's the function that we're trying to average. So I want to first persuade you that if you have an a, like a is 1.0, right, 1 centimeter, and if b is, I don't know, like 1.5 centimeters, Mathematica is pretty powerful. So it can just tell you what the answer is pretty quick. .16. Okay. Mathematica is also, so what would that mean? If error 1 is about a centimeter and error 2 is about a centimeter and a half, if these are two-dimensionally randomly distributed and they add up vectorially, your typical error is going to be about 2.16, which is less than them added, just as scalars. So the drag about this is that we only have a measurement for one specific pair of error magnitudes. So let's quit the kernel. So that clears out the memory. And let's just see what this integral is. So you can either write it out with all the fancy math symbols, or you can just type out integrate, square root, right? Let's just do a shift enter and see what it is for any A and for any B, right? Formulas are almost more useful. Well, I shouldn't say always. Formulas are useful, and variables are and numbers are useful, right? But formulas of variables allow you to design. So power. This is not an easy integral for Mathematica to figure out. If it was, it would be done, right? But it's still thinking. So while it's thinking, I want to show you how you can do this with Excel. Mathematica, if you're in the business world, costs about $1,000 maybe. Everybody's got Excel. So in Excel, you can do the following. You can make random numbers. So I'm going to make a random number. Okay. To do that, you type equals and random. Oh no, rand. There, 0.34. Now this random number goes from 0 to 1. Now I want to make a random angle that goes from 0 to 2 pi. So I'm going to take this number, so I typed equals, and then I went over, I multiply by 2, and I'm going to multiply by pi. Well, Excel doesn't know what pi is, but there's a pi function. All right, so we got a random number and a random angle. Here, I'll show you what pi is. Right, 3.14. Notice that every time I enter the keystroke, I get a different random number. It's wild. Okay, so now I'm going to enter in my my radius. So the magnitude of R. So, oh shoot, you know what I need? I need to know what A is, and I need to know what B is. So I'm going to say A is 1, and B is, I'm trying to remember, 1.5. Okay, so R is equal to, I'm going to try and do this from memory, the square root of A, so I'm going to click on this cell, squared, plus B, click on this cell, squared, plus 2 times A times B times the cosine, capital cosine, of my angle. And so it's kind of fun. It's almost like putting together some kind of Lego, right? Because in my equation, I'm referencing all these other places on it's called a spreadsheet. So all of the different cells have numbers, and I can make references between them. Super powerful. I'm going to close it up, hit return. And so now this right here is my formula. So this is A radius. Now, if you think about actually drilling holes in the circuit board, we could just do this. We could have the machine drill 1,000 holes in the circuit board. And if we drilled 1,000 holes in the circuit board, we could just figure out on average what this R is. So I'm going to go from 8 to 26, right? That's maybe 14 different instances. So 14 different holes that I just drilled in the circuit board. And so I copy, so I'm going to highlight all these and then do Control C copy, and then I'm going to do Shift down, Control V paste, and then, oh, that's kind of weird. Shouldn't this be a radius? Why is it 0, 0, 0 value? What's the cell reference here? Oh, okay. So now you see that my formula pulls on the random angle, so that makes sense. but it's not grabbing A and it's not grabbing B. And that's because I forgot. So sometimes you want these cell references to move, and sometimes you want them to be anchored. If you make it $B and $3, $C and $3, if you put dollar signs in front of that cell reference, then they're anchored solid. So now I can copy and paste. Oof. So now my numbers make more sense, right? Because they're 1 or 2 or 0.9. Okay, that makes more sense. Now, as a check of my answer, I'm going to find the averages for each of these columns. So I'm going to find the average of, so let's find the average of all these random numbers. Now think about it. What should it be? The random numbers go from 0 to 1. So 0.5 wouldn't be horrible. Yeah, and it's pretty close to 0.5. Okay, so the average of all of these angles, so 0 to 2 pi. So 3.14, that's what I expect. And we're close to that. I mean, certainly within 10%. So now the average, I don't know what to expect. Average of all of these radii. 1.7. 1.7. What does Mathematica tell me? Oh, still thinking. Mathematica tells me 2.16. It's pretty far from 1.7. Okay. Let's highlight all this, and then let's go down, I don't know, a long time. So like 1,000 holes drilled in circuit boards, that's a lot of holes. So I'm going to copy all that and paste it. So Control C and Control V. And then I'm going to change this average so that it goes from here all the way down. So copy, paste, paste. Now look at that. We expected the random number to be 0.5, and it's super close. We expect this to be pi, and it's super close. We don't know what this is. Mathematica says 2 something, but we've got 1.66. So this is more common than you'd think. So we got to check our answer. So let's look at this radius. Let's look at the formula. So B3 squared. So B3 squared. So B squared plus this cell, C3 squared, right? So we've got A squared plus B squared. That's what this term is and this term is. Plus 2AB cosine theta. What's the big deal? Let's go back to Mathematica. A squared, B squared, 2AB. Look, that's what we missed. So let's copy this, paste it everywhere. Now our experimental measurement says the average R, right, that number right there, 2.162. Mathematica says 2.165. So I feel good about that. All right, so 2 different ways of finding the average value of a function. Way number 1, do an integral in Mathematica. The region over you're integrating, you integrate from start to finish. You integrate a function over a variable, and you get a number. This is called the average value theorem. It's a thing in Calculus 1. I'm sure you'll hear about it. The other way, generate a whole bunch of random numbers. Turn them into random, independent variables, so random angles. Try your function out for every one of those random variables, average the result. Notice you get the same answer, 2.16, 2.16. Notice as well, Mathematica is still thinking. Hasn't come up with an answer yet. That's because this is some crazy elliptical integral, and it's going to be a nightmare. I think I could give it all night and Mathematica wouldn't figure it out. That's it.